afternoon, everybody. Thanks. Welcome, everybody, to our Forum 360 panel discussion on the future of aerospace design. We're especially interested in exploring the role, too, that digital engineering plays in today's aerospace design community, and hopefully this afternoon with an eye toward producibility, too. I'm pleased to be the moderator for today's discussion, and I'm especially thankful to the panelists we have on the stage, as well as our panelists online, for joining us and being here to participate in what I think promises to be a very exciting discussion on the topic. My name is Jesse Quinlan, and I'm with the NASA Aeronautics Research Mission Directorate. I've spent the past decade of my career supporting our advanced concepts groups and conceptual aircraft design groups at NASA. Today, though, I serve as the Strategic Technical Advisor in the Advanced Air Vehicles Program Office, where we lead the design, development, and testing of low to mid TRL technology supporting next generation air vehicles, spanning subsonics, supersonics, hypersonics, as well as vertical lift applications. The work that our office does routinely requires integration of cross-disciplinary requirements and methods and models, often combining design with optimization and uncertainty quantification, systems engineering and model-based systems engineering, as well as research and testing. And hence, our work in AAVP and in NASA Aeronautics, and I would say certainly the work of the aviation community at large, really lends itself to the application of digital engineering methods and tools and techniques really throughout the product life cycle from start to finish. And before I have each of our panelists introduce themselves, I'd like to describe how we conduct this session this afternoon. We're going to have about 10 minutes for introductions at the beginning, and then we're going to split the time that we have into 3 focused discussion areas around themes that we felt were relevant to the future of aerospace design. The first of those themes is going to explore what it means to bridge the gap between design, technology, and testing, and especially what it means to do so digitally. The second area is going to explore what it means to work together across the engineering, enterprise, and life cycle, hopefully with the support of digital engineering. And the third theme, especially with an eye toward our future and what I would argue is our community's greatest asset, and that is our people, really what it means to develop the digital workforce of the future for aerospace design. So we'll try to spend about 15 minutes on each of those 3 topic areas to be sure that we have plenty of time at the end to take your questions from the audience. And so I encourage you, we'll have a QR code that flashes on the screen throughout the session. Please go ahead and submit your questions, and we'll try to feed those into the discussion as we go, and at least at the end, try to get as many of those as we can. So with that, let's go ahead and start with introductions, and I'd maybe ask Ray to our right to go first.
My name is Kolonay. I work in the Aerospace Systems Directorate in AFRL. Currently, I serve as a senior scientist for advanced structures. Prior to that, I was the director of the Multidisciplinary Science and Technology Center, and I also have some industry experience. I worked at GE's Corporate Research and Development Center for about 6 years. My background is mostly multidisciplinary analysis, design optimization, structural dynamics.
Thanks.
All right. Good afternoon, everybody. Karl Hutter from ClickBond in Carson City, Nevada. ClickBond, for about 40 years now, has been a leader in supplying assembly technology, both processes and hardware, to the global aerospace industry, primarily at the OEM level, also at the operator level for MRO and special missions upgrades and things like that. And we are the pioneers that really brought the crossing of the streams of mechanical fastening and adhesive bonding to the aerospace industry a little over 40 years ago. So I'm the proud second-generation leader and CEO of my company for the last 10 years. And I'm really excited for our Act 2 that we're really in now. And it comes at just the right time with all things digital as we're exploring this week. And that is now crossing the streams between the physical and the digital. So over those 40 years, we've gotten this amazing front row seat, both in the shop floor and in the hangar, around how human beings, incredible human talent, need to use great information to execute process-critical assembly and maintenance techniques. And we really believe that there's an amazing opportunity to harness that digital thread that everybody here is working so hard to develop and unify, and use that to connect our human talent for the next generation, both training and work execution, to both be able to leverage that digital thread for confidence and excellent work output, but then also feed back to it using their very human eyes, ears, and hands and the tools that they hold. So very proud to be carrying the manufacturing torch on the panel today.
Thanks, Karl. Jim, to my left.
Jim Walton. I work for Lockheed Martin. I'm a Lockheed Martin Fellow for Conceptual Design, which is where most of my background is. Currently a chief engineer on a major program that's in production. So between conceptual design and where I'm at now, I've kind of seen all the problems we create as conceptual designers and how they manifest on the shop floor. And so I get yelled at on both sides. But I'm here hopefully to express that kind of perspective.
Thanks. Karen?
Hello, my name is Karen Feigh, and I'm a professor in the School of Aerospace Engineering at Georgia Tech. And I am a cognitive systems engineer, which means I'm a human factors person. And that usually means that I spend a lot of my time thinking about humans interact with different digital systems and avionics and AI these days. But here I am on this panel, I think, to represent academia and workforce development and how we are preparing our undergraduates and graduate students to take on the next generation of designs.
Thanks. And Kenneth, online.
Yeah, good afternoon, everyone. Ken Senechal from OSD, Office of Secretary of Defense, Research and Engineering in the Developmental Test Evaluations and Assessments Group. And we're looking to leverage the power of digital engineering to really transform how we do acquisition holistically across the entire spectrum, from upfront mission engineering analysis, understanding the capability gaps, all the way through operation sustainment, using the power of digital engineering to really provide for a continuum of tests. So rather than tests showing up at the end of an acquisition program, taking too long, costing too much money, and only providing bad news, really test is a structured way to provide for decision makers throughout the entire continuum. And so as we look into the conceptual design phase and anchoring in mission engineering, we'll talk more about this in a little bit, saying, hey, as I do those design trades, let me take those in a digital environment and go execute my ultimate flight test against those designs and say, hey, how does this design impact the flight test? How does that flight test actually link back to the mission? Am I able to accomplish what I need to accomplish to get the job done? And so bringing all of those pieces together is what we're trying to do in this digital environment. And we're also working to facilitate not only talking about the concept, but realizing the concept. We've been hosting a number of events. We just had a hackathon, and to clarify, a hackathon is not a cyber event. It's an event where we get a bunch of people in a room to work to a common solution together. And we did exactly what I just described. We linked mission engineering, system engineering, and test. We're looking to bring in specifically discipline engineering at our next event next year, but we're able to pull from that mission, design a test, execute that test, feed that data right back up to the mission level to say, hey, are we closing those mission gaps? Yes, no. So looking forward to the discussion today and the time with the panel. And I apologize that I can't be there in person. I'm in the DC area, and of course, right when I get ready to fly out, we get a major storm. So I apologize, but I look forward to the discussion. Thank you.
So let's go ahead and move into the first theme that we want to explore here. And that is the intersection between design and technology and the digital, really digital engineering. And the first question I'd like to ask the panel is, how would you characterize the intersection of design, technology, and testing? And especially, how would you characterize this intersection given your perspective in your organization today? Maybe we'll start at the right here.
Happy to start. In a lot of the work that we do, we're developing this process that we'll call effectiveness capability development, and we're merging MBSE with the MDAO with the mission engineering or military utility. Whenever we're trying to evaluate a new technology, we'd like to know how that technology impacts mission or military utility. Now, we often model the technology in the MDO environment, but there are times when it's easier or quicker to actually carry out a test to get the responses of the information that you need in the design environment. So instead of trying to run a high-fidelity simulation, we can quickly 3D print something and get it into a test fixture and get the information we need for our design studies to evaluate the technology all the way at the mission level. So that's one way that we use testing. The other way is that whenever you start testing further downstream, we want to use the physics-based analysis or design information to guide us in testing. We're never going to eliminate tests, that's not realistic. But what we want to do is pick those places where we have a lot of uncertainty in the results that we're getting from our design and test in those particular regions to validate not only our designs but our methods.
Yeah, I think I'd like to add into that I think there's a pressure in a lot of current programs to move as quickly as we can. And when you do things like there's wind tunnel testing, large-scale wind tunnel testing, there's a certain amount of timeline that's unavoidable in terms of model design and build and getting into test and getting that data out. That a lot of times, at least recently in my experience, by the time you get the data back, it's almost too late. You're then in kind of a Band-Aid mode because the loft has been frozen, and woe be the engineer or the aerodynamicist who says, gee, I think we need to update the mold line. They tend to get marched out of, well, they used to get marched out of the chief engineer's office, now they get marched out of my office. But because change later on in the program is extremely expensive. So finding a way to get some of that practical testing in, which is, the digital testing is incredibly important. We can get a lot of insights into it like a lot of people know. But getting practical, very focused testing on specific technologies that you can do relatively quickly, early as possible, is critical to actually marching a design forward that's going to close with a minimal amount of change, the expensive change late in the schedule, late in the program.
Good point. Karl, Karen, would you like to?
Yeah, I mean, it's interesting because the folks, I think this question is primarily directed at are my customers, and you're thinking about how do you get ahead of things with lots of zeros and very long timelines, and recognizing that. But the version that I kind of bring it to in our own world, really I think of some very specific manufacturing techniques that we use for some of our components. So one of the things that ClickBond is kind of wizards at is precision deep draw. And we have an amazing team in Connecticut that can turn stainless steel and titanium metal strip into amazing geometries with very high precision. Where I'm going with this has traditionally been a very black art. It is 4 generations of amazingly skilled craftsmen and tool makers basically doing this by trial and error and tribal knowledge passed down. Like, well, if you want to try to move, Nisencoat strip that far in 2 stations, you kind of got to look at it this way, son. Okay, that doesn't move at the speed that modern design needs to go at. So we're really excited to be doing our version of digital engineering, test, and evaluation concurrent with product design and manufacturing engineering around this. So it starts with characterizing the material in this case and really understanding how to model this seemingly humble material. So call it A286 stainless steel strip. But the variability of that material lot to lot exceeds what you can control with a spec. So how do you, an industry ASTM spec, so how do you characterize that, model that correctly, do empirical testing, stress strain analysis on the raw material, and use that to design tool and die progressions to turn something from strip to complex component over 15 stations of draw. And that's where we're really focused. And I think it's just a microcosm of the bigger conversation around moving from something that was generational tribal knowledge, wisdom passed down, or a lot of very expensive testing and iterative evaluation, and trying to converge the art with the science and bring modeling to get that fire on target faster and reduce that iterative time and cost. So maybe just an anecdote from a different aspect of that.
Yeah, great. Interesting point. I want to hold on to some of the discussion around tribal knowledge and institutional knowledge and maybe try to weave that into our second theme as well. I think it's going to be very germane there. Karen or Kenneth, anything to add on this first question?
I was just going to say that the vast majority of the faculty in my department and probably aerospace departments across the country, this is what drives them. It's like, how do we get this next level of insights with the new stuff coming out with between AI, generative AI, machine learning, and things like this, and improve them and put physics into them? Because right now they're just a lot of regression techniques writ large, but trying to really embed the physics so that you could use them and be practical and reduce the number of times you do have to put things into a wind tunnel or you do have to go stress test them.
Yeah, and I'd certainly like to chime in because I think this is very much where we're going, and I don't know. I'm going to try and share my screen. I don't know if this is going to come across. It looks like it's sharing there in the room. I can get it to play, but this is exactly where we want to go from our initiative, the dT&E as a continuum. Because again, here you see, and this is what's already been talked about on the stage, as we talk about going through those conceptual design stages. In this example, right, we're changing our plan form, we're changing our engines. This design is linked out to physics-based models that is replicating the mission we're trying to fly. So I make a design trade, I go and execute my test point that I've already built that's linked to the mission. I go see how that impacts. I bring it back and I see what the performance looks like. And I make another design trade, or I make a choice that I want to get at this, at this level. We're talking about the conceptual level. But now we can get into the details. Okay, now as I start to really look at my plan form, okay, how far apart are my spars? What material am I using in my spars? I can link all of the detailed analysis in there. And so the simple change that we used to do in the old days and not really be able to find out how that impacts the broader aircraft, much less the mission until we actually flew it, we can bring that to the left side of the system engineering V and have that discovery up front and early. So again, what I'm showing you is not the art of the possible. This is real. We have programs that are doing this today, and this is what we're trying to institutionalize across the DoD acquisition system as we move forward, right? How do we link mission engineering, system engineering tests? And I think we're going to get a little bit more into this as we go further into the discussion to say, if I understand that mission scenario from the beginning and I, looking at that mission scenario, generate a test that says, hey, if you pass this test, you're mission effective. You're showing that you can close that capability gap, you can execute the mission. And now that I have that test in hand, I can use that test to start to drive my requirements to pass that test. So we get really into a test-driven design philosophy rather than requirements driving tests. Test is driving requirements. And for those of you that are familiar with Agile, right, that's one of the Agile benchmarks, and that's really what we're looking to do is take that out. And now that we can do a lot of this early design in the digital environment, taking those tools to this broader level and really scaling it to help deliver capability at the speed and scale of relevance.
Great, thanks, Kenneth. It's, I think, a good segue into the next question that I wanted to ask the panel as part of this first theme. And Kenneth touched on this a little bit in some of his commentary there, but I wanted to maybe play on a more classical question, and that is the chicken or the egg. But in this case, should testing drive design, or should design drive the testing? And maybe we can explore a little bit the implications on the classical systems engineering V in this regard as well. So who would like to take a first crack?
I'll take the cop out right up front to get it off the stage.
Perfect.
It requires both. You kind of have to go both ways, and it kind of drives off of your original comment, is that when we're doing a large development or something like that, you typically only want to have maybe one or, at a stretch, two miracles that you're trying to resolve. If you try and pack in more, the program's just doomed for failure. So in that one area that you're really trying to solve a serious technical challenge, getting that testing in up front is critical in order to enable the rest of the whole thing to close. But at the same time, you kind of need to have a design in first in order to know what to test. So it is something that needs to be worked hand in hand. But I guess it depends a lot on, I'm copping out on this huge, but it depends a lot on exactly what it is you're trying to, the kind of program you're trying to do, the problems you're trying to resolve, and the kind of testing and how expensive or time-consuming that testing could be.
Anybody want to?
Yeah, I'll agree with that. I mean, it depends on what phase of the program that you're in. I mean, early on, the design is driving the testing. But later on in the program, then you have to test, and that's going to be information that you're going to want to feed back to the design. And hopefully, I think like you mentioned earlier, hopefully the OML is not frozen yet. Because whenever you start freezing things too early in the process, then you start finding late defects in the system due to unmodeled physics, and now you're either extending time, you're extending cost, or worse yet, you're reducing the capability that you were originally trying to get to. So it depends on where you're at in the process, but you need both, just depending at what point in the acquisition process.
Yeah.
I might offer a twist on this, which is mission comes first, right? And so we start with mission, and I say that to differentiate, not from so much a hoo-ha type thing, but to say let's not get locked into our exquisite platform or design, right? Let's think that remember that mission comes first. And I think this is truly one of the great gifts of DT and digital engineering and digital manufacturing is going to be the ability to push off those big decisions, maybe even gasp OML. I mean, there was something called the Century series of aircraft where we just did whole different airplanes iteratively to get to where we needed to go. Maybe we can start getting back toward that because indeed the type of ML and AI enabled test and design ping-ponging back to each other is going to, I think, make that much more efficient in a way that combined with flexible tooling and manufacturing processes that might be much more rapidly adaptable could get us to a place where the great windfall of this digital transformation is pushing those decisions, even ones that today would be incredibly, definitive, further to the right. And at the very least, unlocking the ability to continue to iterate designs over time that go well beyond what we think of as block or spiral development today. Tie in things like open source software and mission systems and all the other elements of this. So maybe, I just would suggest that there's something we can do to push the whole thing to a more flexible, out to the right, less rigid standpoint. And I come back to mission to say that we've seen, heartbreakingly, too many programs that by the time our time span for getting them to the battlefield or into even flight test elapses, the mission has changed. So we also need to think of mission not even as a static waypoint, but as something that's sort of moving in space. And hopefully all these tools will allow us over the course of a shortened, hopefully, design cycle, move to a place where we can stay more locked with the evolving mission as it moves through space-time. But of course, there's another piece, which is the acquisition process, but that's for a different conference. That could be the great bugaboo.
I'll actually agree with you. There's the acquisition process, but there's also risk tolerance, both within the approval authorities as well as within the companies themselves that are putting them together. There's a lot of great startups out there that, I'm not allowed to say who they are. I'm sure my bosses would love me. But Anduril, as an example, that have a different funding approach and they're more self-contained and they're able to go out there and rapidly test and rapidly evolve at a pace that, I'm going to get in trouble, that the primes struggle with because of things like shareholder value and that like I said, risk tolerance. That Century series from back in the 50s, they represented a sea change difference in the way we think about how to move forward from a defense standpoint. And obviously, the threat at the time was a significantly different threat than we have now, although even that's arguable at the moment. But I think the world was far more willing to accept the reality that we had to do that in order to maintain the position we had on the world stage at the time. We have to do that again, but again, that's going to drive a very different way of thinking in terms of how we go about rapidly evolving and building things. We can't do this every 10 or 15 years. We lose the experience. That's into your third topic here, so I'm helping you out. But if we're building an airplane, a major system, once every 10 to 15 years, we're doing it for the first time, every time. And that's unsustainable.
So I'll throw out there, again, thinking about how one of the most important and most challenging things we try and get across in engineering education is a healthy skepticism for whatever comes out of the computer, whatever calculations that you have done. And this will continue to be a very important and vital skill for the future generation of engineers. We're going to have a lot of new capabilities coming along, but somebody to sit back and be like, are all my assumptions right? Did all that come through properly? Where's the risk here if I'm wrong about this, plus or minus 10%, 20%, whatever it is, the miracles that you're talking about? Like, is it really a miracle I'm seeing coming out of that box, or have we put something in there incorrectly or calculated something wrong or made a wrong assumption? And I think that will continue to be an interesting challenge. And it goes on both the testing side and the design side.
Yep.
You know, just maybe a quick note, because I hope everybody loved Ken's great visual there as much as I did. One thing that you'd want to always make sure to have in those models is the manufacturability. At some point when you slide the slider on your great composite monocoque airframe wingspan, you exceed the size of any autoclave on the planet. So there kind of needs to be that TRL level for materials and process systems, right? So if we go too far in this direction, we make a hop from, say, in autoclave to out of autoclave. Well, someone better go check and make sure that that's ready to go on the time frame that your program is. So that's a piece of the modeling and simulation that shouldn't be forgotten as well.
Kenneth, did you want to weigh in on this one as well?
Absolutely, and I thank you for that good segue as well. So I'm going to be the one that steals the chart and shares this. So we had said we're not going to do slides, but we also said I was going to be there live. So, but this is the discussion that we're going to, which is linking mission to system to T&E. And part of my broader spiel is really the core system model, the core T&E model, and the core mission engineering model in an MBSE model is the same model, because we're all looking at the mission the same way, and a mission is defined by the tasks that you need to accomplish to achieve that mission. You need to accomplish those tasks under certain conditions, and there's certain measures we're going to hold you accountable to accomplish that task. So we look at the mission, we link it to the system model, to the test, and out to those other physics-based models, and I love you brought in manufacturing models, all of the different models that are going to play into this to say, hey, can we put all these pieces together, and again, in a multidisciplinary environment, and be able to link those up? Did I just lose the audience? Am I dropped?
Got you, Kenneth.
Okay, I just lost the visuals on you guys, so I didn't know if I was out. But being able to flow from the mission down to the front line, and as the mission changes, which I think is absolutely key, because every one of us is delivering capability for specs that were written 10 years ago. But if the bad guy goes from being able to see me at 100 miles to being able to see me at 500 miles, I need to see that implication. And likewise, I need to be able to see the implication of, hey, the requirement said I need to have a radar that sees a bad guy at 100 miles. Instead, I'm only seeing him at 80 miles. Well, how does that play out against the mission? Let's link that up to that mission level analysis to really understand how that impact works. And then what we're trying to do, and I'm going to build this out quick just to make the point, is really that ongoing knowledge, a campaign of learning as we go through that first understanding of the mission, through S&T experimentation, all the way into acquisition, and ultimately into operations sustainment. You brought up manufacturing, but we really need to be able to continue our learning and operations sustainment. There's a lot of data that's coming from the front line that we can use to incorporate into our updates to our design. But also, as we start to field AI and ML, those systems are going to get smarter or change as they get out in the field, and we're going to need to be able to check in with them to make sure we're not creating Skynet. So we want to be able to support that decision space throughout the entire continuum, starting from model-based system engineering models, linking it to low fidelity, high uncertainty physics-based models, and then as we start to get actual production, actual code, actual representation we can run in the wind tunnel, starting to refine those models, getting them to a level of a digital twin that isn't a no-kidding replication of the system we're testing, and linking all those pieces together. So there's a testing continuum, there's a M&S continuum, and really a data continuum. So we're looking to bring all of those together ultimately to support decisions as we go forward, because to support a decision, you need information. To have information, you need to get data. To get data, You need to get it out of M&S and testing, and to M&S and testing, you need resources. So that if you think about the decision making you need to do, that drives the strategy for your entire continuum as you move forward.
Excellent. Thanks, everybody.
Excellent.
Let's go ahead and move to the second of the three themes that we're going to explore this afternoon. And we're going to pull on some of the things that we heard actually in the discussion for that first theme as we walk through here. But the second area is really meant to focus on exploring what it means to work together across the design, engineering enterprise, and product lifecycle. And the first question I'd like to ask the panel is, where does digital engineering offer the most value to design and engineering? Or perhaps where would you say is the opportunity to make the biggest impact with digital engineering in this regard?
Okay, actually, good. Sorry. I think the biggest one, at least from my perspective, is configuration management. One of the biggest challenges we have is understanding and having everyone on the team understand exactly what is the current configuration that you are designing to, running trades against, developing a wind-tunnel model, because we keep driving to that one. That having a full and very locked down understanding of what configuration, what the state of the configuration is and what assumptions have gone into it, what issues still remain in it, and what we are allowing to change in that current design cycle is critical to actually keeping things moving forward and minimizing the issues that catch us out in the end. It's never going to be perfect, but I think digital engineering and being able to expand that thread across more of the general disciplines that tend to support airplane or vehicle design of any kind, that's one of the biggest things. Of course, the other side of that is when all of that data is available, sometimes it becomes difficult to control how far that data spreads in terms of, well, so-and-so is working on a trade and I think that's the direction it's going to go, so I'm going to alter what my trade is based on what I think that trade's, and then you're losing control again. So sometimes too much data can be a bad thing too, in a lot of ways, but I think, back to my original point, configuration management and control is probably the biggest fundamental improvement that digital threads bring in, at least to what we're doing.
Yeah, I'd like to add to that. So I view that as the authoritative source of truth, and that's in one, say, conceptual location. The other two areas that I think the digital engineering will allow is that, that N-squared diagram that Ken put up there, we've looked into stuff called distributive collaborative design. Not every one of those boxes live in the same organization or the same facility, but digital engineering will allow you to distribute that and execute that real time through the digital engineering process. So that's another way. And then the third way is that if you create a digital thread, the information that's developed and the models that are used at the conceptual or pre-milestone A can follow the system throughout the process instead of, in a traditional process, there's these discrete steps and stops in time where people take their models and they give the information to the next phase, say the conceptual design, and they go back and recreate all the models of the same system because they didn't have the sufficient information from the previous stage, or it's just the way they've been doing things. But I think a continuous digital thread will allow that information and the models to continue with the system throughout the acquisition process. So those are the three key things I see the digital engineering enabling.
Great.
Yeah, I'll throw my human factors hat back on. Also trying to capture the decision-making and the reasoning for certain engineering decisions so that you don't circle the wagon and make a decision, come up with a problem, think about it, and then just keep going around in this cycle because you've forgotten that the reason you decided not to go with this configuration was because of this, but it brings about other problems, so therefore you cycle.
I mean, what you've both just said, sparks this idea in my mind. How cool will it be, and how useful when we have concurrent engineering going on across multiple disciplines on a platform at one time, and there's an an AI agent in there that's actually peeking over everyone's shoulder, getting a sense of where, I think I'd like to go in this direction. Now, I haven't committed that design change or recommended it, but imagine if there's something going, ooh, you know something, if you go that way, it unlocks design space for these 3 other departments. Let's kind of upvote that, right? Or, that's going to start constraining other people based on what we see in their pending design evolutions. There could be some super cool stuff there. 2 things I think that are going to be great value. Maybe to that fact that it takes a village to design an airplane. I think that one of the great benefits and values for digital engineering is going to be sharing the load. So what are the adages? 90% of the cost is designed in at design, so we better take advantage of that time frame, and 60 to 70% of the value or the cost is in the sub-tier. I think the digital engineering has the opportunity to really unlock the participation of industry partners outside the primes and across the tiers of the supply chain, to be able to pass, with all the attendant security bells and whistles, to pass elements of that design in a model-based engineering world to, if you will, the experts on the actuators, on the, hardware and fasteners, on the, various engines and modules and things like that, and basically say, here are your constraints, here's the design problem, go for it, and give me 3 scenarios back, and have that be able to just be a digital-to-digital interchange, I think is probably one of the greatest opportunities to really engage the supply chain and to, put capability against need at that focused way. 2, I think the other big opportunity, of course, is, it was mentioned, configuration control. Absolutely, and I will give the sort of manufacturing or supply chain take on that one. The ability to know how many bolts go in the plug door today. Did that go up or down from yesterday? Did we install those fasteners, and do we have green check marks in the quality management system? The ability to follow the configuration management all the way from the engineering building down through the 4th tier supplier, and be able to have everyone on the same sheet of music from a quality and conformance standpoint, I think is a very, very powerful one for quality and for safety. So I think those are the 2 I'd mention.
Actually, the foot stomp, I want to foot stomp your first point. A lot of times, like when we're designing a vehicle, the engineers have this pie in the sky view. It's like, to close this design, we're going to need this, and we'll talk about an engine. We're going to need an engine that's capable of these things, and we've already chosen Pratt. It doesn't matter. And then hey, we're all done. We've sold it to our leadership. Everybody's happy and slapping themselves on the back. And then we have that meeting with Pratt, and we say, hey, cool, we love your F-135. But in order for our whole story to hold together, we're going to give you an inlet that's got 5% less recovery than you were expecting. We need 10 more horsepower extraction, and we need all of that with 5% better SFC. Let us know when you're done. Because they were excluded from the process up front. Having them involved, and obviously we try and involve the engine companies as early as we can, but as part of that digital thread in the early conceptual design stages, when you're going away from brigade to your first initial kind of, propulsive efficiency, aero efficiency, weight, which is really structural efficiency, and looking at those and assigning where you're going to be putting the risk into the program, and understanding that, and then engaging the suppliers that could actually directly affect that as early as possible with the digital thread, meaning you're getting them in a configuration managed and understood step. I did it twice. Is going to help us immensely.
Excellent. Ken, did you want to weigh in on this one as well?
Yeah, of course. This has been a great discussion, and again, I'm going to share my screen. So you're asking fundamentally, what is the value that digital engineering brings? And I think you've heard it over and over again. Really, and especially as we talk about this testing continuum, it's driving discovery to the left side of the V. And you can see from these early sources, but I would say intuitively, we all know this. We bake so many of our problems in during the left side of the V, and then we don't find them until the right side of the V. This example, this is software built, but I would say this goes to hardware as well, right? 70% of our defects are built in on the beginning. We only find 3.5% of them on the left side. And again, as noted just a moment ago, we're committing 70% of our costs on that left side of the V. So we really need to bring that discovery to the left, and that digital environment allows us, as I showed earlier, to link the mission to the system and to the test. And I think a lot of the discussion here has been, okay, well, around an individual air platform as we move forward from a design perspective. But really, again, if we're talking about the mission, the design trade's at the systems level. And so, I could make a trade within a platform that cost me $1 million or $500 million to make a trade within a platform, but maybe I can still put the warhead on the forehead if I make a slightly different trade. So rather than investing, a $500 million to upgrade the radar on one system, maybe I only need to make a $10 tweak to a missile seeker head in another system and still be able to complete the mission thread as we go along. And that's where that criticality of that connection to the mission, and again, I'm just going to flow this out, but this goes to the discussion that was just made, where we're linking everything we're doing back up to the mission. So as you flow this down, and I did this in PowerPoint, I have a presentation I can show later that actually does this in a digital model, where as I decompose the mission elements to the individual, in this case, it's viewed from a test perspective, the individual tests I'm going to do down to that component level test that will all link back up to the mission. But again, as I mentioned earlier, this really is the system engineering design process where I take that and flow it down. So again, I originally built this to talk specifically to, hey, I'm doing a test for a track and I need to determine the systems I need to go for the track. But to go to the story that was just shared, hey, I'm going to need a certain performance element out of my engine, and so I can flow down here exactly what was just described with recovery rates and all of that, so that Pratt understands from the beginning what they need to be able to build into and how really that links back up to the mission. So if they come up short, we can see what the mission impact, because we allow for this continuity and this linkage of data from the mission all the way down to the lowest level components that are a part of supporting that mission.
Thanks. So I heard quite a few themes come about in the responses to that question. And a couple of them were along the lines of what it means to share the load, capture knowledge, carry the models through the process from start to finish. And I thought maybe we could entertain a question around this in some regard. When we think about how engineering is done and aerospace engineering is done, there's a lot of knowledge contained and often siloed within different departments, different organizations, different groups, different individuals. And I'm curious, how does digital engineering enable new ways of perhaps crossing some of these divides that exist? And also, I think, how does digital engineering offer us new ways to work externally with partners as well, and help cross some of these divides?
I'll go. Again, my human factors hat on. One of the fundamental things about work, when you divide work amongst people, you create more work. It's like thermodynamics, but for behavior. This is how bureaucracies are formed, right? So now if I take my work and I give it to you, we have to communicate. We have to coordinate. That's an added burden. So the amount of direct work that I can do goes down proportionally to how much communication we have to have together. Mm-hmm. If you have well-designed, in my opinion, well-designed digital systems, then you can capture most of my direct work and most of my direct thoughts, and someone else can view them without having to interrupt my direct work. There's a theory here. I've not yet seen it done in practice. My inbox is a testament to this. But I have hopes that perhaps when we all get good AI agents, that I can task my AI agent to go look at somebody else's work and report back to me as how my students are doing on their projects.
And I'd like to add that I think one of the dangers, or cautionary things, is with digital engineering, with all that data available to you, engineers in general from a personality type tend to generally, put the hoodie on, leave me alone in my cubicle, and I'm going to work. And if I have access to all the data, then I'm not going to have to talk to another human being.
This is the dream.
And I can't tell you, I have had more than one occasion where I've had to literally take an engineer who's complaining about someone in my office, and I said, so you're complaining about this person, and you're not getting along, and you're struggling back and forth to make a decision. Where do they sit? Over there. 20 feet away. Let's go. And then we sit down and have a chat, and then 5 minutes, the situation has been resolved. Personality part's probably not, but at least the technical issue that's causing that problem has been resolved. That siloization where we tend to want to do that to ourselves is an ever-present problem just due to the fact that personality types tend to get into engineering. And so that's the one cautionary thing that I'll say is that having, I think I kind of referred to it earlier too, that too much information can be bad, right? If you have all of it at your fingertips and you decide that you're the smartest person in the cubicle at that moment, then you're going to interpret that data how you want and then make decisions how you want without double checking with the person or the team that actually created that data, and then things diverge and go bad.
I completely agree. I think you definitely, if you have only access to the data, you might come to very different conclusions than the person who created the data.
In her presentation this morning, Alexis, the CIO from AFRL, said something that I couldn't agree with more. I think is wonderful. Digital transformation is human transformation. And I think this is really at the core of this, both in terms of the potential and, of course, the challenges of getting there. I think that I got to see firsthand in the last year in an example of a proof of concept deployment of our immersive mixed reality digital assembly work instruction solution that we're working on. We did this, I can talk about because it's out there, at Vertical Aerospace over in the UK on their advanced air mobility eVTOL. And what we gave them was a tool that allowed the placement of hundreds of bonded non-determinant assembly. So, we gave the world at ClickBond the gift of, you can make a systems installation, bracket attachment, or cable tie mount go anywhere you want. We gave you the problem of now where does it go? And so there's been a lot in the last years of templates and things to figure out where do you measure and where do things get installed. So we gave them a solution that let the technicians look through a HoloLens and see the holograms of those components exactly where they should go and stick them right in the correct place. Now here's what was magic about this that really made me light up. I got to see shop floor techs who are working kind of doing their job every day of building an airplane. Get to take this new technology and beyond the questions we were interested in of would they be receptive to it and would it work and things like that, I saw something truly magical, which was that those assembly techs became manufacturing engineers just like that. And what I mean by that is we had a whole pile of parts sitting in the bottom of the fuselage, and they were doing some dry fits just to see if we could align these things closely enough using the overlaid work instructions. And we had one gentleman coming in from one side and another from the other side through what would eventually be the cabin doors of this thing. And there's a pile of parts in the middle, and everyone's wearing HoloLenses, and they're working on the same work instruction. And I saw at one point a guy pick up a part and go reach for where it should go, and it was just too far. And without even a verbal communication, well, maybe it was just I got it, mate. The other gentleman took a piece and stuck it where he saw his friend trying to reach. It was a very simple little example, but it's the power of where we can go with this by bringing more people into the conversation. So whether it's on a physical prototype, whether it's on a digital model, the ability to get people who have the best knowledge on a given subject, in this case, the folks on the front line, at the tip of the spear, folks are going to have to build these things by the thousands if everything goes well. Actually being able to participate. So if you just took that, play version of that digital work instruction and flipped it to record, you would have a proxy work sequence and division of labor, and you flip it to record, and now you actually get the folks who are going to have to do it, basically making real-time proposed edits to that sequence and turning from being and I never use that word that way, assemblers and technicians and turn them into manufacturing engineers. It's just an anecdote that I think highlights the bigger picture, which is there's so many opportunities to do things like that and get non-traditional players really deploying their talent in ways that are really powerful.
Actually, and I'm really happy you brought up the text because the designs we come up with when they're in NX and CATIA and PowerPoint, they're always perfect and they work every time. And then you develop your work instructions and your designs, and then they show up on the floor, and then you got a bunch of techs who want to kill you. Being able to bring, especially in early conceptual design, when you're doing internal layouts and you're packaging the vehicle and you're getting all the boxes in, being able, as part of a digital thread, to be able to include assemblers, techs, electricians, tubing folks, to be able to come and say, yeah, did you think about the fact that we're going to have to route wiring harnesses between these things? And you're actually going to have to be able to get a hand in there to place to place a screw or a bolt and actually get a tool that has some throw to it to actually mount this thing. It's amazing how much an airplane has to grow just because you actually have to physically be able to build it, versus just putting it on its nose and shaking until everything Tetrises down into the bottom of the nose to get your CG right.
So with that, I'd like to segue to our third topic area. We've been talking a little bit about people. And our third area that we wanted to explore was really the digital workforce and the future aerospace design workforce. And we want to explore a couple questions related to this theme. And the first is, specifically we've talked a little bit about institutional knowledge and where it goes, where it resides, how maybe we try today to capture it. What does digital engineering offer us in this regard? Specifically, how can we leverage digital engineering to help maintain that really, really critical institutional knowledge, and especially to help support our new design efforts for new product, new concepts, new technologies? Any thoughts?
I'd love to see it used to come up with some nice case studies. So a lot of times when we hire folks to teach our senior capstone design courses, we go to industry and we grab somebody just stepping out of industry and we say, come, teach our students and tell them all your war stories of what you've learned over the course of your 40+ year career. And that's our way of trying to get some information across. And some people are better at doing that than others, but I would love to start capturing more case studies. And these can be 10, 15 years, so things are a little less sensitive than they were at one point. But to really capture, what were the lessons learned? Where did we almost go wrong? Where did we lose 3 months of work because we made a wrong decision or made a wrong assumption? And try and get that in and distill it, and not just in senior capstone design, but could we have this going through as the students take all of their lab classes? Could we pull those stories that are appropriate for different types of skills that they're learning and embed that into the educational process?
Oh, yeah, go ahead.
Yeah, well, to add on to that, so having all this information, this data from a given program, archive it, make it searchable, and also make that information be available in some sort of context, which is what she was alluding to, is that what decisions were made based on this data, what assumptions were made to produce this data. And then that will enable people that are coming next to be able to use that data. Because right now, this stuff is buried in reports, it's in file cabinets, you have no context of what it has. Even if you can get access to the report, you have no idea how the decisions were made. So I think from that perspective, it can really help the next generation workforce.
Yeah, I think the expert capture aspect is so critical, especially while we're still trying to figure out how to shorten the time spans so you don't have maybe one program in your entire career, and then we do it all over again, as you said, Jim. But I think critically, you said that they're right, we've got to capture why did I make this decision, not just the decision I made from an engineering or kind of when you have knowledge-based work, right? How do you capture the reasoning that went into that? And some of that maybe is captured in people's design memos and reports, and some of it isn't. So we need some really great thinking about how to make it low overhead to capture the why for the future generation. I think there's a parallel on the, if that's the knowledge work side, there's a parallel on the manual work side. I've done some wrenching on legacy military aircraft platforms. You can have all the TOs in the world, tech orders, and follow the instructions to a T, and you're just going to end up cut and frustrated. There's a lot that you learn on the job about, but that's what it says in the book. What they don't say in the book is you got to go up this way first. And if we can capture those things also, I think that's going to be one of the great gifts. But I think the reasoning and the why has to get in there, not just the 1, 2, 3.
Yeah, if I could chime in on that, just because as we've been talking about this design support evaluation framework, which is really kind of the foundation of what we want to take as we go forward, really understand what are the decisions I need to make as I go through a program, through this acquisition continuum. And again, to make those decisions, I need information, I need data, I need to go test it or model it, and I need resources. And so you can link all of that together in a framework, and that framework we're using right now is an MBSE model. We've captured one that we're working to mature and to grow, and if anyone out there needs an MBSE model for how to go do T&E and how to link it to ME and how to link it to SE, we've got it available, just reach out to me. But to that point is we've got that framework captured, and we can understand how that information flowed up to support those decisions, and we snap those instances in the model. And as brought up earlier, right, a lot of the information we've done previously to make decisions are a PowerPoint file that's on someone's laptop that's been forgotten about 10 years ago. Now we've got that ongoing authoritative source of truth where that information resides. It's available. Not only that, as we go into future generations, as we lay out some of these models, like I said, I've got a model that links together mission engineering, system engineering, test. No one else needs to go recreate that model. We don't need to reinvent the wheel. We've created it. It's now available for use, and you can tailor it to your specific need, but now you're only doing 10% of the work where you used to have to do 100% of the work. And as we've developed more of those models for here's how you test air warfare, here's how you test surface, here's how you test strike. If we've got those foundational structures built, they're now available as we move forward, right? You just need to take that, tweak it to your individual use and go forward. And I'll even expand on that. We were, if you saw my slides, they're tagged for NDIA because we presented at NDIA, the National Defense Industrial Association, the end of last year. And the question to the industry was, hey, do you want a common reference architecture coming out of the government? And the answer was an overwhelming yes, because if each program puts out a different model in an MBSE environment, then each industry partner needs to retool to match up with that model, as opposed to just having a common reference architecture that we're all working to. Here's what that architecture is going to look like. Here's how the mission and the system are going to be contained. Now you can bring your specific industry solution to bear. So not only is there value from handing on that information to future generations, but there is an impact and a value to how we do business today.
Ken, could I ask you a question on that? Do you think that while we wait for and hopefully we'll get some grand standard taxonomy and standard for this kind of rich data, but we can't wait for it, right? Do you think that there's a role that ML can play in the meanwhile as a translator from my structure to your structure, from unstructured to structured, et cetera?
Yeah, absolutely. I actually was talking with one of the AI/ML leaders about that, and there's the idea that if I've got an MBSE structure, that we have an AI/ML that can go in there, data mine out the original ontology taxonomy, and be able to build a translator ring to be able to connect it to other models. Absolutely, that is something that we're talking about. I don't know if we've got any software programs that are going after that specifically, but I know there's some that have that in their queue.
Excellent. So I'd like to ask one more question on this third topic, and I've been tracking the audience the audience submitted questions, and the highest voted one, I think, weaves in very nicely to the last question I want to pose to the panel here in this third area, and that is, what's the most important feedback or advice, again, thinking about the students that may be in the audience and the junior career or junior staff that could be in the audience here, What's the most important feedback or advice you might give to that next generation of digital engineers and aerospace designers? And I would add to this, especially with the rise of autonomous systems and AI and ML, and that's a nod to the highest voted question from the audience right now.
Well, for people that want to get into the area of, well, say, design or multidisciplinary analysis and optimization, I think you have to have a perspective of both breadth of the entire system all the way going from the mission. We talked about, the mission is the primary thing, and all the way down to manufacturing. These are things that you have to have some breadth of understanding of. But not only that breadth, you have to have some depth in my opinion, at least one technical discipline, be it structures, be it aerodynamics, controls, or whatever it is. Because without that depth, you're not going to understand the silos and the depth that you're going to need from the other disciplines if you're trying to develop this system. For the perspective of AI and ML, I don't know who made the quote, but the thing that resonated with me, AI is not going to take your job, but the person who uses it will. And so that's from in terms of using AI to do design. That's my view on that anyway.
Thanks.
Okay. And my perspective from early on, I would say that MDAO brings the progress, the prospect of being able to capture more potential variables and try and fold those in early in the conceptual design. And just all of a sudden we're trying to, in an MDAO or an optimization model, we're trying to optimize 60 different variables, and we're going to try and design the airplane in the first shot by just hitting the big button and letting it run 10,000 data points, which is absurd. I will speak specifically for airplane design, but airplanes generally are sized by maybe 2 or 3 of what I call the big knobs from a requirement standpoint. And then everything else are kind of fine-tuning things. The early stuff is about finding out using common sense, which I believe is about 80% of our job. What are those primary knobs that are driving the airplane design? And it's usually just 2 or 3 things. And then using MDAO, once you've identified and got the airplane figured out, is it a biplane or is it a flying wing? Once you've got that fundamental set of choices made and you understand generally what the vehicle is going to look like, then you start smartly, common sense, layering in more and more of those details. I don't need to know what the specific horsepower extraction down to the horsepower is as a trade when I'm trying to figure out how many wings I have and how many engines I have. I need to know generally what's my propulsive efficiency and about how much thrust I need. That's about it. After that, how I get there is a bunch of trades downstream. Once I've figured out that I've chosen an engine that's an achievable place, or an achievable thing technically. How we structure bringing in the MDAO so that it's being done at an appropriate level of fidelity as a function of time is the biggest challenge, because right now we have a lot of students, I'm going to shift this way a little bit. We have a lot of students from colleges everywhere that come in saying, I'm going to just run my big MDA model, submit it on Friday, come in on Monday, and it's going to tell me what my optimum design was. And they have it spit up a number if they're lucky and didn't crash, but they have no clue why that number is the way it is. Yep. And if we smartly run through those sizing trades, the engineer will understand what's driving that design, what the sensitivities to it are, and then can stand up in front of leadership and say, well, what if some idiot like me says, well, what happens if you don't meet your aerodynamic L over D, cruise L over D assumption? They can actually think on the spot because they understand the perspective or the sensitivities of that design to the L over D that they assumed and answer that question versus saying, wait a minute, I'll have to get back to you and then go through reams of data they should already understand. Siphoning out the 650 other variables that they didn't need to run while they were trying to come up with the answer.
Yeah, I think that understanding why that's your answer is going to become even more important with the awesome capability that's going to come with the ability to crunch all those variables at once. It's like your elementary school, or middle school teacher, math teacher told you, is your answer reasonable? Like, best way to check your work. And are there enough zeros or too many? it's going to be that on steroids. So absolutely understanding the context of what are we really doing here and how do things work and why do I have that answer is key. The one I will add, and I think this is a wonderful thing about aerospace to me, is that given the complexity of the work that we do and the scale at which we do it, there are going to be human beings, talented human beings like the students in this room today, involved in the building and fixing of aircraft and spacecraft for a long, long, long time to come. And that's an amazing thing. Now, that being said, what does that mean that you need to be sure to gain in your studies and in your internships and your experience? Well, one, you need to be able to actually communicate your ideas with human beings. Whether you do that verbally, whether you do that in good writing, good technical writing, whether you draw something, like with a pencil maybe even, if you can communicate it on a whiteboard or over a cup of coffee, you're already halfway down the field, all right? You need to be able to communicate well with other human beings and, of course, with the computers that are going to be helping you. But, and Peter Thiel says this really well, the AI, the automation, all of this stuff is complementary to the human effort, not replacing it. I mean, in certain areas, of course, we know where it will be, but the humans are going to be involved for a long time. The other thing I will say on that front is make things, fix things, understand how you actually might go and build these designs. Turns out that the mouse, I don't know if they do you still use a mouse? I mean, I'm dating myself a little here, and I'm only 25 years in career. The mouse turns out to be an extremely capable but very deceptive tool. I had the benefit and the joy of growing up in a machine shop and seeing and touching and doing a lot of these things. And as I was saying in the green room, by the time I got to UPenn in '96, they were moving the machine shop equipment out, and that made me very sad. You got to go out and actually understand how the things you design are going to be built and sustained by actual human beings.
Yeah, you can tell in an instant when an engineer has actually worked with their hands on anything. Even if it's a lawnmower, you can tell in the way they do the way they go about design and integration. And it's the ones who have actually worked with their hands, have done design, build, fly experiments, who have done anything with their hands, grew up on a farm. It doesn't matter. They have a huge leg up in being able to have that practical common sense knowledge and being able to apply it towards designing something new.
So I'll add one more thing, especially if you're still in school. Go make friends. Find people who are smarter than you in disciplines that are different than yours, because you're not going to be able to know it all, right? You need to be technically depth in your area, but when you're thinking, I'm a controls person, I need to understand something about structures. You need to have a person that you're going to call and say, hey, can you sit down with me for 10 or 15 minutes and just walk me through why this is a challenge, right? Somebody who can explain things. I'll build on that. So while you're in school, these people are easy to find, right? And they're usually, you can take them for lunch, you can have a cup of coffee with them, you can do whatever your university does. Ours does like donuts and things like this with grad students, and find them and talk to them like, hey, you're in so-and-so's lab. What are you working on? What are the big interesting problems in your area? It don't have to be your big interesting problems, but at least now you're like, oh yeah, that is an interesting and big problem. I'm glad I don't have to work on it. But you're aware of it more. You can go to other disciplines here at SciTech. Like, let's just go to a different technical session.
Great. Ken, did you want to add on?
Yeah, no, and I'll be brief because I know we're running out of time. But as someone who actually took a mechanical drafting with paper and pencils when I was a freshman in college, which definitely dates me, there is really understanding that you need to get involved with this digital engineering environment. So even if you're a classical aerospace engineer like I am, taking a class to understand model-based system engineering, to understand those tools is going to be vital as we go forward, because really having that as a foundation for the work that we're doing. If you haven't already seen it, I mean, we've got a whole section we're talking about here. Every forum, every conference that I've been involved with for the past several years have been about digital engineering. So make sure you get the technical background and knowledge to go along with your core aerospace engineering knowledge. to move forward into the work you're going to be doing in industry.
Yeah, well put. Excellent. We have a few minutes left. That's the end of the third theme we wanted to explore here. We have quite a few excellent submitted questions online here, and I would love to try to get to at least maybe one or two of them with the panel while we've got the time. We hit one or two of these in that last discussion, so I'm going to go down the list and ask a pretty interesting one here, may elicit some feelings. So design is often mentioned as both an art and science. As design becomes more digital, and especially with MDO regularly being used to refine designs, is there an expiration date on design being an art?
No. So I'll talk to you later. He was actually ratted out by her, so it's all right. Art, in the conceptual design phase for airplanes, again, I'm going to be very airplane myopic about it. There's a million ways to draw a curve or a line that defines the upper profile center line of a vehicle. I can't stand the mouse and the computer for that reason, because what tends to happen is we tend to just do an extrude or do something that looks really ugly. And there are examples in our 20-ish maybe year history where some things had some aesthetic challenges and some others had some little less aesthetic challenges. And it mattered. Setting aside the technical stuff. But one of the things that, as part of my fellowship, I work with a lot of the conceptual designers, except him. I'm not going to work with you anymore. One of the things we try and drive is that you have a million different ways you can draw that curve that defines the upper profile of an airplane. Well, Mother Nature has, and this is all art, so just bear with, Mother Nature has been optimizing birds and fish and things that move through medium for millions and millions of years, and there's a reason why they look the way they do. Who are we to say that we know better than Mother Nature? And so when you are designing something, yes, you can draw that straight line, and it may be super simple to design it, and the hinge lines may be super tight, and your doors may be super easy and super small goosenecks and everything else, but it looks ugly as hell. And so even putting in, a 1,500-inch radius, something that's just practically flat from an engineering perspective, but your eye will catch it, and it'll look like a curve. And things will look more organic. That artistry, and one of the things I drive, thank you, one of the things I drive is long before, in the early conceptual design phase, long before you reach for the mouse when you're doing like how many engines, and is it a flying wing, is it a two-body tail, is it, all the different kinds of ways you can draw an airplane, is to reach for your pencil. Yes. Pencil and blank sheets of paper and literally sketch them out. Plan views as quickly as you can. Yeah, none of us went to art school, so they're going to look like crap. Mine too. But they're notes. They're just quick notes about all the different ways. Are the engines in the back? Are they in the center and buried? Are they apart? Or is there a weapon bay or a payload bay in between? Or is it split apart? All the different variations of all that. You can draw that with a pencil and a piece of paper and a sketch pad. You could draw hundreds of those in a day, or 50 or 30. And then lay them all out there and actually with people, because you actually want to talk to people, have them come around and actually start identifying which ones make sense and why I kind of like the idea of this with the idea of this. Let's put these two together and come up with it. There is an art to that process of coming up with an optimization long before you start the MDAO optimization of what you think the airplane is going to really look like. And that's one of the ways that you can bring in some of the experienced folks that have been around industry and have built a bunch of things in their past. Well, they've got all that stuff locked in here, and they're probably not going to be reaching for a pencil or a CATIA mouse anytime soon. So how are you going to get it out of them? Show them stuff, because they love to critique. We love critiquing. So let us critique. We'll critique, and I call it seagull mentorship. You come in, you poo on everything, and you fly away, and they have to solve it. But people in my age bracket love to do that. We love to spout our knowledge. So that is a whole artistic process in and of itself, to be able to having that organically flow and get it out there. Then you can reach for the mouse and draw a pretty airplane. it's got to be pretty. If it doesn't look pretty, it's not going to work.
Got to be pretty. Do we have one more opinion on that question?
I think it's an art. All the other stuff are just tools to help the designer spend more time thinking than doing other mundane stuff. And maybe the tools may take them into a place in the design space that was counterintuitive to them. That's all it's used for. But it's really an art, in my opinion.
Excellent. With that, we're just about out of time. I just wanted to thank everybody for joining us this afternoon, and especially thank our panel for being with us. Let's give our panelists a round of applause, please.